Thanks. The mic's working, right? Okay. I'd like to begin by thanking the organizers for giving me the opportunity to speak here, but more than that, giving me the opportunity to come to this wonderful city. It's been an absolute delight. I'm going to talk about some work that I've been doing with my collaborators at Oxford and Edinburgh on the study of scattering amplitudes in curved backgrounds, like curved gauge field backgrounds and curved spacetimes. So I'm a mathematical physicist. So the main question or mathematical curiosity that I've had is, it's not working. Huh? Oh, okay, good. I think it works now. Okay. So the main question that sort of sits at the background of these set of efforts is fairly basic. We observe a lot of emergent simplicity in the study of, in the mathematical structure of scattering amplitudes. That follows from many modern methods like on-shell recursions and stuff. So one might very naturally ask whether this simplicity is accidental, as in whether it's an accident of being in flat space, because flat space is maximally symmetric, and you can use gauge symmetries and unitarity cuts and all those good things in flat space. Or could it also extend beyond the flat space scenario? Could it also extend to interesting curved backgrounds, like, for example, cosmology or ADS or black hole backgrounds? But at first glance, the on-shell methods that we commonly use, like BCFW recursion or unitarity cuts, they seem to appear highly specific to the structure, the rational structure of propagated denominators and things like that, that are present in flat space, but could have more complicated functional background dependence in curved backgrounds. So it seems pretty hard to just naively extend on-shell methods beyond flat space without using some action principles. And the idea that me and my collaborators have been developing for the past, well, since 2018, 2019, is that twisted theory, at least, can provide one way of going beyond flat space. And the hope is that the methods that we get from twisted theory can then be used to generalize other on-shell methods. So in the past few years, we have studied a particular toy class of backgrounds, which are known as self-dual backgrounds in both gauge theory and gravity, which have allowed us to do many concrete amplitude computations. In the gauge theory case, so it's a bunch of papers. I'm just sort of citing a cross-section of some of the papers here. In the gauge theory case, we have many tools available now. We have tools like twistor actions that can be used to derive CSW type recursion relations, if you're familiar with that kind of thing. And these recursion relations can be extended in a systematic way as the Feynman rules of certain off-shell descriptions of these theories in twistor space, of Yang-Mills theory at least. And that can be used to compute concrete all multiplicity, at least tree-level amplitudes in self-dual backgrounds. For gravity, we have some similar tools, and these tools will be the focus of the talk today. So we have developed a tool that's known that we've called the twistor sigma models, which is basically developed along the lines of sort of copying the ideas of twistor string theory. And this tool can be used to compute tree-level MHV graviton amplitudes on certain self-dual gravitational backgrounds. And I'll explain this today by way of the example of a self-dual black hole, the same kind of thing that Alfredo was talking about yesterday. Okay, and there have also been many interesting, perhaps to me, unexpected interplays with celestial holographic methods that emerged over the course of my grad school, which I was very pleased by. So now we can also use celestial holographic methods and two-dimensional CFT techniques to compute amplitudes in Iguchi-Hansen space and Bern space and many other interesting self-dual backgrounds that are, again, toy models of more realistic backgrounds, or could have applications to string compactifications. And Roland might mention some of that in his talk. Okay, and I would also like to give a shout out to numerous other modern approaches that people have been developing over the course of the past decade or so to compute amplitudes in many other type of backgrounds, like trying to go beyond self-duality or trying to do more physical type of backgrounds like cosmological correlators and anti-de Sitter space holographic boundary correlators and stuff like that. And of course, there's the example of scattering on black hole backgrounds that all of you have been studying, many of you have been studying, and has been mentioned in this conference. Okay, so now let's get to the tool that I promised you all describe. A twisted sigma model is basically a two-dimensional CFT that we motivate by means of twistor theory. So without going too deeply into the twistor theory, let me just say that this is going to be a 2D CFT that allows you to compute MHV graviton tree amplitudes. The structure of this 2D CFT is fairly simple. It's an integral over the sphere with a bunch of poles in the measure. And the poles in the measure, so lambda is an integration variable, while there are a bunch of spinors in this measure, 1 and 2, which get identified with the spinor helicity variables of the negative helicity gravitons, which I'll scatter shortly. And the rest of the action is actually a fairly well-known CFT called a beta gamma system. So this mu naught and mu 1, secretly being twistor variables, are just some bosonic 2D fields, which will have a 1 over z minus w type propagator. And this is the kind of thing that you encounter, for example, when studying the ghost systems in string theory. Just that in this case, both mu's will have conformal weight half. So just by itself, this would correspond to a 2D CFT that computes amplitudes in flat space. To turn on background, we deform the 2D CFT action by some other interaction term, which encodes basically the data of the SD gravitational background, the self-dual gravitational background, on which we'll study the scattering process. And using these, we can compute MHV graviton tree amplitudes as connected tree-level correlation functions of this 2D CFT. And I'll give the example of the Taub-Nut case shortly. So, but just to show the results, for example, if I set h to 0, I can compute a certain correlation function in this 2D CFT that recovers for me Hodge's formula for the MHV graviton amplitude in flat space, where you might be familiar that the Hodge's formula is a determinant of a certain Hodge's matrix with a bunch of rows and columns removed, and times some free factor that ensures the correct little group scaling, among other things. And going beyond flat space, we can do interesting self-dual backgrounds. So the simplest self-dual background beyond flat space happens to be source-free self-dual backgrounds. So just pure self-dual gravitational wave profiles. And these are known as self-dual radiative spacetimes, which are purely determined by their asymptotic shear data as some kind of initial data that you put at null infinity. And when you plug in this particular value of h, which is determined by the asymptotic shear, into this 2D CFT, you can compute amplitudes on these backgrounds as well, as we've done in this paper that I invite you to look at. Today, I want to use this twistor sigma model to study scattering amplitudes on a toy model of a black hole, which is known as self-dual Taub-Nut space. So let me remind you that Taub-Nut space basically has this line element where it depends on two parameters, the mass, m, and something called the nut charge, capital N. Schwarzschild, so this object is a generalization of the usual Schwarzschild geometry. You can also turn on a spin to get Kerr Taub-Nut. The Schwarzschild case is obtained when you set n to 0, so that you only have a mass parameter in the game and no nut charge. And as many of you might know from experience, computing scattering amplitudes on Schwarzschild or Kerr is a pain immeasurable. You have to do a lot of things like solve the Tucholsky equation in great detail, and those equations turn into complicated Hoyne equations that you basically die solving. Or, there's a separate case you can take where instead of setting the nut charge to 0, you can set the nut charge to a value that makes this metric self-dual. So self-dual just means to say, if somebody doesn't know, that the Riemann tensor of this metric is equal to its Hodge dual in some appropriate sense. What self-duality does is, it basically imbibes the spacetime with the structure of some integrability. And when you study theories and scattering amplitudes on self-dual backgrounds, the amplitudes and even the scattering states become drastically simpler than their more physical counterparts, like the actual Schwarzschild case. So what I'm going to do is I'm going to think of this case as a toy model of a black hole. And I'm going to show you how easy it is to compute scattering amplitudes on this background. So the first step is to go to Euclidean signature where this metric becomes real. So you have slightly more control on the kind of space-time integrals that you get in scattering amplitudes. And when you bit-rotate the Euclidean signature and do a mild coordinate transformation, the metric takes the form of a Gibbons-Hawking metric. And I've set the net charge to be I times m, so the only parameter now is this capital M, which is like an effective mass of this geometry, you can think. The first remarkable result that really surprised us, and which we originally found using twistor theory, but in hindsight you can do variable separation and find it as well, is that you can solve the wave equations on this geometry in closed form. So Alfred also harkened back to this yesterday in his iconal scattering amplitude type expression. So basically the idea is that when anyone computes scattering amplitudes, they first have to solve for wave functions of external free fields, which in flat space we take to be plane wave states, but in a different geometry, they have to be appropriately modified so that they solve the wave equation, the free field wave equation in that geometry. And trying to do this in Schwarzschild is terribly hard, but we realize that in this other case of n equals minus im, you can solve for these wave functions in complete closed form. No Hoyne functions, no hypergeometric functions, no Meyer-G functions, nothing required. It's all very simple. It's just the flat space wave function. So for example, I've written here the example of a spin 2 state, which is a graviton. So I've just given you its, so this is a negative helicity graviton field strength, which is its Weil tensor bit. In flat space, the plane wave states that you usually scatter would be a plane wave e to the ik dot x times a bunch of undotted spinners in the negative helicity case and a bunch of dotted spinner helicity variables in the positive helicity case. So I hope that's you have come across before. And in the Taubnut case, all that happens is that this simple plane wave state gets dressed by a prefactor that makes sure that the wave equation is satisfied in this curved geometry. Quite nicely, this state is still labeled by a null momentum, which is a null momentum in completely the flat space sense. K alpha alpha dot is a null momentum, which splits into a product of negative helicity spinner kappa and a positive helicity spinner kappa tilde. And there are some other parameters in this state. This parameter Q, which basically, well, this state solves the wave equation for any value of Q. But if you want to avoid branch cuts, you have to set Q to equal 2m omega or minus 2m omega. And that gives you either positive frequency states or negative frequency states. And all this is just details. You don't need to remember all this. And the only other thing of interest is that in this geometry, in Euclidean signature, this is a Euclidean black hole, so time becomes periodic. You may have seen these cigar type pictures for Euclidean black hole. Because time becomes periodic, the frequency, the eigenvalue of the momentum in the time direction also becomes quantized. And the quantization here just depends on the period, and the quantization rule just becomes 4m omega belongs to integers. And so when Q is either 2m omega or minus 2m omega, the branch cuts in this wave function get avoided. Okay. So all that just to say, in summary, that we can find the states in closed form. Once you have the plane wave-like states that you can imagine scattering, you plug them in your on-shell action at tree level to compute tree-level scattering amplitudes, or your path integral with some boundary conditions to compute loop-level amplitudes. So let me give you first the example of a minus two graviton tree amplitude. Because of the self-duality of the background, the plus plus and plus minus amplitudes continue to vanish, but the minus minus amplitude gains a non-zero value. To compute the minus minus amplitude, you take the state that I showed you on the previous slide. You can manipulate the on-shell action of Einstein gravity so that you only need to plug in the values of the spin connections associated to the field strengths I showed you on the previous slide. And computing the spin connection as a potential is a standard process. So you can do that again in closed form, but I won't show you here. When you do that, you can derive this 2-point amplitude. So you plug in the values of the wave functions in this integral, and then at least at 2 points, this integral could be done in closed form, which my collaborator Giuseppe Bonia managed to do, which is rather nice. When you do the integral in closed form, you get an answer, which is very simple, again, expressible in terms of certain rational functions. And complicated or not, the most interesting part of this answer, the most interesting feature, is that we've managed to compute it non-perturbatively in M. So for example, M occurs inside factorials. This factorial is fine because 4m omega was an integer, and inside powers. So that's the most important feature. Usually, when you compute amplitudes of probes scattering off Schwarzschild or Kerr black hole, you only do it linearly in M or quadratically in M, like in some of the talks discussed here as well. But the self-dual backgrounds are simple enough that you can actually do this computation in closed form in M. So this is still a tree-level amplitude in the usual sense of the word, but it's non-perturbative in the geometry. To go beyond 2 points, we need to use pistorial technique. And that's where the twisted sigma model two-dimensional CFT that I had mentioned previously comes into play. And this is a paper to appear shortly. So the twisted sigma model associated to a self-dual Taub-Nut background is the model associated to flat space, plus that gravitational perturbation I had mentioned. The gravitational background perturbation associated to Taub-Nut can also be written in closed form. It's very simple, and in fact was found in a completely unrelated work on harmonic superspaces and stuff like that, if you've come across that, in '86 already. So all we needed to do was plug in this representative into the technology that we had already developed and compute certain two-dimensional correlators. And I don't want to go into the details of the vertex operators used, but the structure is fairly simple overall. The MHV amplitude is given by, you first compute a correlation function of a pair of vertex operators associated to the two negative helicity gravitons, and n-2 vertex operators associated to the positive helicity gravitons. And then you have to do an integral over Taub-Nut space by hand, which you can do in a straightforward way. So this is a general structure that computes the scattering amplitudes. There are specific expressions for the vertex operators of the states that you can write, that you can find in our paper. But let me just finish the talk by flashing the final result that comes out. And I'll just tell you just the rough structure of this final result. So the MHV amplitude, and this is an all multiplicity tree-level MHV amplitude of gravitons on self-dual Taub-Nut, again, non-perturbative in M. The MHV amplitude that we find has the following interesting features. Taub-Nut space doesn't have translation symmetry, so momentum conservation gets replaced by just a more restrictive energy conservation bit. There's still an energy conservation symmetry because there's a symmetry along rotating along the time circle. So there's a delta function in the frequencies. There's a factor that's reminiscent of the Hodges formula that was sitting in front of Hodges determinant. And then there's a leftover integral over the spatial direction of the self-dual black hole, where you get a bunch of plane wave states, which is familiar, but you also get a factor that comes from the metric determinant that basically tells you that the background is curved. Again, if M were to be 0, then this would just reduce to a momentum conserving delta function. The next bit is a prefactor that basically comes from that dressing, that gravitational dressing of the flat space wave functions that that I showed you earlier, a bunch of products. And then there are a bunch of integrals that come from doing so that I showed you a 2D CFT. When you compute correlation functions in this 2D CFT, you have to do various Wick contractions, and you have to keep that interaction term, that fourth order interaction term in mu that I showed you in play. When you keep it in play, you do all the Wick contractions and you compute the correlation functions. You get some extra integrals generated, one integral for every insertion of that interaction vertex. So this is just like 2D Feynman rules. This is nothing fancy. All I'm doing is a perturbative computation in a 2D CFT. And then you get a complicated formula where you get a Hodges matrix which depends on certain parameters, epsilon and eta, which you can think of as parameters that encode gravitational wave tails. So whenever you scatter a graviton off a curved background, most of the times the gravitons can scatter against themselves. And what that does is it generates factors of gravitational wave tails. And these tails again show up very explicitly in this background. So there's a Hodges matrix, which is actually a slightly larger matrix, which depends on some parameters that encode the strength of the gravitational wave tails. And we have to basically take some derivatives and extract some bit of this matrix. Some of the other features of interest is that we encounter something called the incidence relations of self-dual Taub-Nut. So if you are familiar with twistor geometry, or if you've heard of this in other talks, in twistor space, we encounter certain incidence relations that relate the twistor coordinates to the space-time coordinates. So the incidence relations of self-dual Taub-Nut, so basically without these exponential factors, you would have the incidence relations of flat space. And to get the incidence relations of the twistor geometry of self-dual Taub-Nut, you just dress with simple factors, and these things directly enter the formula here and here. And there's a background deformed Hodges matrix. So this has a factor H, which is the Hodges matrix familiar from flat space. And it has some off-diagonal entries which encodes the gravitational wave tail scattering, because you're sort of generating new gravitons. And even in the original Hodges matrix, one of the more interesting features is that because of the self-duality of the background, the angle brackets don't change. Angle bracket contractions remain undeformed, while the square bracket contractions, the square bracket spinors are sort of self-dual, so the self-dual background affects them, and they get deformed to some structure that I won't talk about in more detail, but basically there's a spin frame on the dotted spinors that multiplies everything, and you just get a slightly background dependent square bracket. Okay, so let me finish by mentioning some other work that we did on the single copy of the self-dual Taub-Nut background. You can also study the single copy, which is given by a self-dual Dion background, which is also fairly simple to write and is also self-dual, so it also manifests some integrability. And the MHV amplitude, which is the analog of the Park-Taylor formula, can again be computed on this background in closed form. In this case, you get a conservation of energy, you get a conservation of total charge. There are some charged particles that are scattering in the self-dual gauge field background, and you get a Park-Taylor factor, which still comes out very nicely. This, to me, shows that the simplicity in scattering amplitudes at least manages to persist beyond flat space, at least in these self-dual backgrounds. And the hope in the future would, of course, be to try to go beyond self-duality. And there was a great result in one of Alfredo and Uri's, one of the papers that Alfredo mentioned yesterday, where he managed to find that Schwarzschild can be written as a perturbation around the self-dual black hole background, but also the Laplacian of Schwarzschild can be expanded around the Laplacian of self-dual Taub-Nut. So you can find the states on Schwarzschild itself, like the scattering states, the plane wave type states, as a perturbation around the states that I showed you that solve the wave equation on the self-dual point. So this should be very interesting to explore, in my view. And then you might also imagine that there might be non-perturbative contributions to graviton scattering that you have to include in your scattering amplitudes in flat space. And an analog of this will be discussed in Roland's talk, but for the gauge theory case. And analogs of this were studied by Hawking, Page, and Pope ages ago when they studied amplitudes on space-time foam and more exotic geometries. It should be interesting to see whether the amplitudes on Taub nut and other instantonic geometries can be thought of as non-perturbative corrections to flat space graviton scattering. Okay, thank you very much for listening.